Hello, class. Welcome to Chapter 2. We enter into the actual calculus lesson. And in Chapter 2, we will discuss about limits. Just before that, I want to quickly describe what calculus is. Why should we even learn about this? And what is the whole study about? Okay. So the word calculus, okay, in Latin actually means a small stone or a pebble. Okay. And, and then the calculus is basically a study, it's a mathematical study of change. Let me write that there. And why is it a pebble? So when we say change, we're talking about, a very small change. So like pebble size change, right? That's what it technically means. So it's actually focused on, instantaneous rate of change. So at every moment, right? So that small, every moment there will be some change. But when I say moment, that time is really, really small. The change in time is really small. So we're trying to see how do the quantities vary over change. And so calculus can be broken into two broad study categories. So we have the differential calculus. And then we have something called the inferential calculus. Okay. Did I say inferential? I'm sorry. Integral. That's because maybe I got confused with the statistics lectures that I'm building. Okay, so you have descriptive and inferential statistics there. So they sounded so similar here. Sorry about that. And you got inadvertently a short stats lesson. So you get two for the price of one. All right. Differential calculus focuses on the study of instantaneous rate of change. And again, this is something very familiar to you, rate of change, right? Rate of change is basically a slope, the rate of change. Okay. And your integral calculus, this focuses on the areas, okay? Areas of irregular shapes. Why irregular shapes? Because if it's regular shapes like a square, a triangle, a trapezoid, a rhombus, these are geometric shapes. So we have, algebra has helped us, geometry has helped us determine these areas for us. So these are predetermined, there are predetermined formulas to help us through those. But when it comes to irregular shapes, which is how it appears in real life, what is the area of those irregular shapes? And that is where calculus comes in handy. And for these reasons, it's really, really highly sought after. What's really cool is that these ideas can be extended to any field. So don't think just if it's area, it has to be something physical, okay? Or if it's instantaneous rate of change, it always means something is moving in terms of time only. It could be time is the most common one we use in real life, right? How did something change over time? So that is there. But even if you keep it in terms of time, you can see that you can talk about business. How did the profit change over time when it becomes business or financial stuff? You can draw trend lines. You can see how did this disease progress over time, and then you get into sciences, particularly now when we're talking about pandemics or epidemics. You like to see how things changed over time to understand their rate of growth and the speed of growth, and so on. So we see that it's uses in so many fields, so many areas. It's not just restricted to sciences. It's expanded and used in humanities, social sciences, um, you know, other history and geology, and so many other places other than the typical science fields that we learn. Okay, so this is why we will talk about the rate of change, which was what we learned related to lines. And so it's actually using what we know to discover things that we don't know. So that's really, really powerful here in calculus, because it's entirely built upon algebra and trigonometry. So you really have to be super strong in these. So we will now go into the introduction on limits. For that, I want to go a little bit over average rate of change and connect that with our calculus concept. All right, so we start with average rate of change, and then we will take you to the instantaneous rate of change. Average rate of change, as you can understand, is over this time interval, or over this particular interval, how did it change on an average, right? But instantaneous would mean at every moment, how did it change? So that will be the crucial difference between the two. So to get to instantaneous, we start with average rate of change. So let's consider y equals f of x, okay, some function. And this is a function that we are interested in over this particular interval, x1 to x2, right? And to kind of give it a visual perspective, let's say your graph looks like this. Okay, you want it to be a curve. Okay? You don't want it to be a typical line. Okay. So let's talk about this line. Okay. So let's call this P. Let's call this Q. Okay. So you're trying to connect the 2 points P and Q through a line, and these are 2 points on your curve. Okay, this curve is your y equals f of x. And to make it a little more clear in terms of the x1 and y1, okay, this will be your x1, this point, x2, and correspondingly, this will be y1, this is your y2. Okay. So if I wanted to find the rate of change, the average rate of change from x1 to x2, right? So in this number line, although your graph could be extending further on, we're only looking between P and Q. What was the rate of change between the 2 points P and Q? If it is a line like the purple line, right, we can definitely find the average rate of change by simply finding the slope between the 2 points P and Q. But remember, here too we're drawing a line, yes, between through P and Q. However, this line is not the line of interest, really, because we're trying to find between P and Q the curve, not the PQ line, right? Therefore, when you try to connect 2 points on a curve and draw a line through it, that line, we call it as the secant line. Okay. So if you find the slope of this purple line, that becomes the slope of the secant line. Okay. So what is the slope of the secant line? This is how we represent it, okay? Slope of the secant line would be m subscript secant, so that you can see that we're focusing on this particular purple line, because I could draw another line, passing through 2 other points, and I'd like to know which ones I'm talking about and so on. So we really want to make that very clear. So, the slope is rise over run. That's the most, colloquial way of saying it. But we know that that is change in y, right? Change in y, that's your rise is your y, over change in x. And the symbolic representation for that will be this triangle, y over triangle x. This triangle is actually a Greek letter, so it's known as delta. So delta y over delta x is a shorthand way of saying change in y over change in x. Okay. And if you recall the slope formula, it was y2 minus y1 over x2 minus x1, right? We all remember that. And we can see that here. y2 minus y1 would be this distance, right? y2 minus y1 is the distance between y1 and y2. x2 minus x1 would be this distance between x1 and x2. All right? So, and this is the slope of the secant line, because the secant line is a line that connects 2 points on a curve. So it's called a secant line. Now, if I were to write this in terms of function, okay, y and x are very trivial algebraic way, but we want to see them as functions. So I want to write the y2 as f of x2, right, because we know that is your y2, minus f of x1 over x2 minus x1. Right? So this is our general formula. So this is basically the slope of the secant line. And it's a numerical value. Okay. Now, in calculus, what we'd like to do is just view it slightly differently. Okay. By that, I mean that if I would consider, instead of x1 and x2, okay, let me choose a quick color here. So instead of x1, I'll simply call it x. Okay. It's again blue, so that's not a good idea. We'll go with the perhaps green. So I'm going to call this x1 as x, and this x2 will be x plus h. Okay. Meaning from x, you travel the distance of h to get to the next point, x plus, which is x2. So x plus h is your x with an increment of h. Okay. So I want you to understand that h is this distance h. Okay. So correspondingly, your y1 would be f of x, and your y2 will be f of x plus 2, because you're no longer using x2, you're calling it x plus h. So if I were to rewrite this formula, x2 is now x plus h, right? So that will be f of x plus h minus f of x, because x1 is now just plain x, divided by x2 is x plus h minus x. You can see that the x's will cancel off. So you basically have f of x plus h minus f of x over h. So that is the calculus way of representing it, because we like to see the h as a small increment. Remember, small, pebble, calculus. So we're talking about h as a small interval. So this x2 could be this distance apart. It could be just so close to x1 that, you know, your h will kind of determine the distance between the two. And h could be a small distance between the two, a large distance. But remember, in calculus, we're always interested in small distances. Okay. Over that small interval, what was the change? Because again, remember, we are using average rate of change to drive home the idea of instantaneous rate of change. Instantaneous is every moment. So we want the distance between two moments to be really, really small, right? Only then you can get the instantaneous moment, the rate of change. Okay. All right. So what we see here is that we are using the slope of a line to define the slope of a curve. Right? So in that process, here is how I'd like to kind of describe the whole scenario in front of us. Okay. Now let's look at this as a curve, right? This is a curve, and a line that passes through this curve is called the secant line. So let's do that. Okay. So this is P and this is Q, and that's a secant line. Now, remember that we are looking at the slope between two points on the curve, and therefore we have the secant line. Now, if I'm interested in finding the slope not between 2 points, but at a point on the curve, okay? So let me, I should have used a different color. Let me use a different color, okay? Hold on. So I'm going to keep the P and the Q, but I'm going to tell you that I'm not interested in finding the slope between P and Q. I'm interested in finding the slope at P. Okay, so if it's at P, you know, it's like basically I have to draw a line just touching that point P and the slope at that point, right? Are you with me on this? So if you're trying to draw the curve, in fact, if I were to stretch this curve some more, you notice that the point just touches the curve, and you cannot be touching other points, right? You just touch the point with your line, the pink line, just touches the point P, on the curve. So now your secant line is no longer rendered useful because it's between 2 points, but this pink line is just at a point because it's touching it. It's tangible. We call this as the tangent line. What is the pink for this? Tangent line. The orange line, we call it the secant line. Okay, it's between the 2 points. So then our job is to move this Q. Okay, so this is how we think in calculus. If it's between P and Q, you have a huge range of values in between that will fluctuate the rate of change, right? But we want it just at that point, and that is the idea of instantaneous, just at that instant. At that point, what is the slope? Then we are trying to move this Q closer and closer and closer to the P. Okay. Because you have to keep the Q on the curve. So basically what you're trying to do is you're trying to connect P and the Q that's moved. Yeah? Can you see what I'm trying to do? You can see how the lines get really closer and closer and closer. So at one point, your Q is this close. Okay, and it's gotten a little messy there. Let me remove those. So you've come this close, and then you're moving it closer and closer and closer to a point where you want to almost imagine that this Q got so close to the point where it coincided with the P. So the P and the Q are so infinitesimally close to each other that it's as if your Q coincided with the P. And that is the idea of limits. You're moving it so close to get from a secant line into a tangent line. Okay. So then the whole idea is there's no longer two distinguishable points P and Q. Rather, the Q has coincided with the P, that there is only a P. Right? So if Q approaches P, P closer and closer, there are no longer 2 points but only P. And so your secant line now becomes a tangent line. If you go back to this slope formula, right? Remember, we defined H to be a very small distance between the two x values. So if your P and Q are no longer distinguishable, but they are almost the same point, that means that your H actually is very, very close to 0, right? Now, if H is equal to 0, what happens to this fraction? That makes it undefined, right? And it renders the whole concept useless. So in the idea of limits, we do not say H is 0. We'd rather say H approaches 0. So it's getting so close to 0. It's not yet 0. It's not becoming 0. Therefore, the concept, the idea of using the secant line as a tangent line becomes acceptable, right? And so your slope of the secant line could actually be used as slope of the tangent line because we are saying that H gets very, very close to 0. So we're developing on the idea. We'll get to that. But I would like to do a quick problem here and help us to kind of understand how to write the equation for a tangent line and so on. Okay. Let's read the question. Find the slope of the parabola y equals x squared at the point P of 2, 4. Write an equation for the tangent to the parabola at this point. To drive home this idea, I'm keeping it very simple. So I've given you a very simple function, y equals x squared. So as I mentioned before, you have to be pretty good with your graphing so that we have a visual of what this means. A little below. So that's your y equals x squared graph. And we're interested in this particular point, 2, 4. Okay. I'm going to try this. And they're saying, find the slope of the parabola. It's not slope of a line, but slope of a parabola. Parabola is a curve. So we're asked to find the slope of this curve at the point 2, 4. Okay. So, we just saw that the slope of a curve would be the slantness of the line, right? Slope is the slantness of a line. So if it is at a point, you want to draw a line at that point touching. Let me see if I can draw it more solid. Should be a fine line, but I just want to make sure that you can see it. So that line is touching the curve at that point, and they called it P because they said P is 2,4. And so this is now my tangent line. They did not give me 2 points. If they gave me 2 points, and if I were to draw a line through those 2 points, it becomes a secant line. But here it's through a point, and therefore it's a tangent line because it touches or it's tangible at that point. I keep insisting on this little bit because it's the first lesson, right? So it's a good idea for you to get that idea ingrained, the difference between secant and the tangent line. And they want us to find the slope of the parabola at this point. And at this point P, what is common at P is that pink line, right? That's the point that's common to both the purple curve, the parabola, and the pink line, the tangent line. So 2,4 is that common point. So what is true on the purple would be true on the pink, and what is true on the pink line would be true on the purple, just because of their commonality at that point. Therefore, we are going to use the tangent line, and because it's a line, we can talk about its slope or the slantness, and we're going to use that information to write the equation for the tangent to the parabola at this point. Okay. So we have only 1 point, but how do you write the slope formula with just 1 point, right? Slope formula works between 2 points. You need the x1, y1, and you need the x2, y2. So how do we use the other point? So let me write a little story here so that we'll remember that. Okay. So I'll just say we are given only 1 point, which is 2,4. So we build the other point as, now remember, you're building the other point, which is a hypothetical point, but then we know that that point is slightly away from this point P, right? Very, very, very closely, very close to P, but it's a little away from P by a distance of h units. That h could be any value, right? Technically, that h has to be a very, very small value for our given problem. So what we're doing is we're just going to say, well, the other point is 2 plus h units away. Okay, so 2 plus h units away. So that has to be 2 plus h squared, because this is x comma x squared, right? That's your y. You with me on this? So we have 2,4, which is a specific point. But then if you're building another point, you're using a variable, an h. Okay, h is actually a constant, but h can vary. That's what I mean. A varying point, so that h can be adjusted to whatever value we want. That h could be, let's say, 5. So 2 plus 5, so it's 5 units away. But remember, we want it to be so close, so 5 makes it really far off from the 2. So I'm thinking h could be 0.1. So it's 2 and 2.1, right? 2 and 2.1, so a distance of 0.1. If I want to make it even closer, I can make h as 0.01. So it'll be 2, 2 and, 2 on the x-axis and 2.01 on the x-axis. So there's a distance of that h is really, really small. And so your h can be adjustable in that sense. Okay. So we already have p. It's 2.4. And we built the q, which is 2 plus h, 2 plus h squared. Okay, always substitute the y coordinate to be the formula, the equation. So y equals x squared, right? All right, now with these 2 points, we can find m secant, because you need the 2 points, right? Secant slope. So that's going to be delta y over delta x. You can actually use the formula from above, right? y2 minus y1. So y2 minus y1 over x2 minus x1. Of course, you expect the 2's to go away because it's a distance of h. Then 2 plus h the whole squared. Remember, it's not the same as 2 squared plus h squared. Know your algebra really strongly. So use either the a plus b the whole squared formula or multiply it twice and FOIL. Either ways, you'll get 4 plus 4h plus h squared minus 4 all over h. And remember, my job here is to teach calculus, not algebra. You've learned algebra over many years or multiple semesters now. So you really want to go back and refresh. Okay, multiply them and FOIL it. Okay, so now we have 4's cancelling off. Right? And by default, you will always have an h, because you remember, we want your h to be really, really close to 0. You don't want any distance between the p and the q. You want them to coincide. So if your h is 0 in this fraction, if h takes the value 0, this will make it undefined. So in this setup where you build the other point, you will always find that the constants will cancel off, and you will find a way to factor out an h. So in this case, I can factor out an h from these two terms. That leaves me with 4 plus h in such a way that the h's will cancel off so that you don't have the dilemma of allowing your denominator to go to 0, right? So anyways, so we have m secant coming out as 4 plus h, okay? Now q is an arbitrary point. When I say arbitrary, it is something that we hypothetically created, right? So, and also arbitrary here would mean that we don't have any fixed value for h. H is adjustable. And because of that situation, that point h, right? Let's come over here. So your q could be further up the curve or below the curve, because h could be anything. It could be positive, negative. It could be the left of p to the right of p. And so we have that flexibility with h, okay? So q could be to the right or to the left of p. So in other words, if h is less than 0, right, if h is negative basically, because you're actually thinking about what this 4 plus h actually means. So if h is less than 0, it means that q lies to the left of p, right? If h is negative, that means your 2 plus h, okay, would basically be 2 minus something because the h was negative. So it will be to the left of p. And if h was positive, meaning it is more than 0, it's positive, then q lies to the right of p. And that's what we mean by arbitrary. We don't know really where this will be. However, remember, we want q to coincide or approach p. It doesn't matter if it approaches p from the left or from the right. We want it to approach p to the point where we really want the distance between p and q to become 0. Okay, so that the distance between p and q becomes 0. Becomes 0. It is we want it to approach that point. Okay. So this means that the secant line, right, would approach the tangent line. That makes sense, right? Because again, let me give a quick description of that. So now we have P and Q. Okay, that's the secant line. And if the Q is moving, along these points, and say your Q is right there, can you see it's beginning to, the slope is almost turning, the secant line is almost turning into the tangent line. So the secant line becomes the tangent line. That's what this description means. Move that. And this means that h approaches 0. Remember, this single arrow means approaches. H approaches 0. Okay. And if h approaches 0, slope of the secant line now becomes slope of the tangent line because the secant approaches the tangent line. And 4 plus h, and we just said that h approaches 0. So the 4 plus h actually reduces to 4, right? So then we get our slope of the tangent line is 4, because thankfully now you can let your h to become 0, right? And because of that nice setup, we always expect an h to be factored out to cancel off with the h in the denominator. So the dilemma is removed, and now you can allow your h to become 0, thus giving us a numerical value without the h. Okay. So we have the slope, and then we have the point, which is given to be 2, 4, because that's where they want us to find the tangent line. And so now we can use the slope point form, again back to algebra, which said y minus, remember tangent line, so it's a line. So you're using the formula related to the line. Y minus y1 equals m times x minus x1. So you have m to be 4 and your x1, y1 to be 2, 4. Remember so y1 comes first, so you have to plug in 4 first. So just bear that in mind. So I'm just going to leave those spaces to plug in. That's 4. M was also 4. 2. Okay. Now distribute this and rewrite this in the slope-intercept form. So we get what? Y minus 4 equals 4x minus 8. So y equals 4x minus 8 plus 4. Right? Add 4 on both sides. And that gives us 4x minus 4. And that, my friends, is your equation. Go back to the question. Write an equation for the tangent to the parabola at this point. So you come back and say this is the equation for the tangent to the parabola. Equation for the tangent. TGT for tangent, okay? Tangent line at 2, 4. Okay? So this kind of describes to you how we moved from secant line to tangent line by allowing the second point to approach the first point. And by doing so, you were able to convert a secant line into a tangent line. And tangent line actually helps you to find the slope of that particular line at that particular point, which gives you the slope at a point which is the same as instantaneous rate of change. Okay, so your average rate of change has now become instantaneous rate of change, and that is really how we move with the limit idea that is to be explored in this chapter. Okay, so hope you enjoyed that and the concept here. And as always, please understand that this is an explanation of the concept, so you'll have to go to your homework problems to work on them, to get the hang of it and to practice more of these types. Okay, I will see you in the next video.